A flute and saxophone play the exact same pitch and volume. This physical ripple in the air represents the identical raw data hitting your ear, yet your brain instantly distinguishes the two. The distinction is so immediate that we rarely stop to ask how two metal tubes can produce such different results from the same note. This is timbre, the tonal color of an instrument. It is determined by the fundamental pitch stacked with a unique spectrum of higher frequency overtones and partials. Because both instruments are essentially metal tubes fueled by human breath, the source of this harmonic fingerprint must be hidden in the physical structure of the tubes themselves. Musical identity is the result of microscopic geometric physics. The specific way a sound wave vibrates inside the instrument's body determines its entire character. Wind instruments function as one-dimensional acoustic rooms. Sound waves travel down a tube, strike the boundaries at the ends, and reflect back. When the reflected wave interferes with itself, it creates a standing wave with fixed landmarks, nodes of zero pressure, and antinodes of maximum pressure. A flute is open at both ends, forcing a node at both boundaries, resulting in a wave twice the pipe's length. This 2L geometry provides the mathematical space to support a full spectrum of both even and odd harmonics. However, the flutist provides a gentle, continuous stream of air. This excitation lacks the high-pressure transients needed to wake up the higher harmonics. The combination of open-ended math and gentle air produces the flute's signature sound, a pure, fundamental dominant profile with a serene, hollow quality. The saxophone presents a physical contradiction. Its mouthpiece acts as a closed boundary, effectively creating a closed-open pipe. In a closed-open system, the wave must have an antinode at the mouthpiece and a node at the bell. This forces the fundamental wavelength to stretch to 4 times the pipe's length. This boundary rule is restrictive. It mathematically limits the pipe to only odd harmonics. If the saxophone followed these cylindrical rules, it would sound muted and limited. Instead, it produces a massive, bright, and complex spectrum. The saxophone bypasses these limits because its body is constructed as a flared cone. This conical taper forces sound to propagate as expanding spherical waves. This spherical expansion shifts the pressure nodes, tricking the physics into behaving like an open pipe. This restores the 2L wavelength and unlocks the full set of harmonics. This unlocked spectrum is then hit by the saxophone's excitation, a stiff cane reed that generates high-pressure, transient-rich pulses. The result is a rich, buzzy timbre, the direct product of a conical shape unleashing a full spectrum of violently energized harmonics. Every musical instrument functions as a time-varying acoustic filter. The physical body of the instrument acts as a machine, shaping chaotic raw pressure waves into organized harmonic signatures. Historical instrument makers refined these geometries through centuries of trial and error, carving precise physical boundaries long before the underlying physics were mathematically formalized. When we listen to an orchestra, we are hearing the invisible physics of geometry physically sculpted into art.